Hello everyone, this is Dr. Webb and welcome to this abstract algebra video. And this is a big one. This is the one where we're going to bring in the last big piece of the puzzle, the Galois group. So let's start marching on. Okay, so let's start off by talking a little bit about field automorphisms. So hopefully you remember the concept of automorphism from when we talked about groups and rings. So an automorphism is an isomorphism. In this case, we're talking about field automorphism, so it's an isomorphism from a field to itself. So we say that sigma is an automorphism of L if it is an isomorphism from L to itself. So that means that sigma is a one-to-one and onto map of L, and that it plays well with the operations of the field. It's a field homomorphism. So for any two elements, alpha and beta in L, sigma of alpha plus beta is going to equal sigma of alpha plus sigma of beta, and sigma of alpha times beta is going to equal sigma alpha times sigma beta. So it is a homomorphism that's an isomorphism that's going from the field to itself. If you take the set of all the automorphisms of L, it is usually denoted aut L. So aut L stands for all the automorphisms of L. We are particularly going to be focused in on automorphisms that don't move some subfield of it. And so if we have K is a subfield of L, we say that an automorphism of L sigma is a K automorphism if for any element of K, sigma doesn't move it. Sigma sends it back to where it was. So for any C in K, we have that sigma of C equals C. So the way that we normally talk about this is we'd say that a K automorphism fixes the elements of K. So the fixes means it doesn't move the elements of K. It just leaves the elements of K alone. So this is something that we've looked at in the homework. We've talked a little bit about before, but if L is a field that contains the rational numbers, then every L automorphism is going to be a Q automorphism. Field homomorphisms that over fields that contain the rational numbers, the homomorphism doesn't really change the rational numbers. It fixes the rational numbers, and so, or at least it sends it to something that's isomorphic to the rational numbers. And so when we're thinking about automorphisms, every automorphism is really a Q automorphism. If sigma is a K automorphism and alpha is an L, and alpha in L is algebraic over K, well, then since sigma is a homomorphism, this means that alpha is going to be sent by sigma to some other element that has the same minimal polynomial as it. So alpha and sigma and alpha will share the same minimal polynomial over K. So the big result in this that's going where things are really going to be building off of is that if you take K as a subfield of L, well then the set of K automorphisms of L, so the set of all the automorphisms of L that fix all the elements of K, this set with functional composition forms a group. Forms a group just in the same sense of when we talked about groups early on in group theory. So this actually is pretty simple to see. So K automorphisms are closed. So if you take the composition of two K automorphisms, you're still going to have an automorphism of L, and if neither of them move any elements of K, if both of them fix elements of K, when you compose them, they still are going to fix elements of K. And functions, by definition, essentially, are associative. And so we get that K automorphisms are closed and associative under composition. The identity element of this group is just the identity map, the map that sends everything to itself in L. This is always an automorphism. And also, since automorphisms are isomorphisms, any isomorphism has an inverse map that's also an isomorphism. And so this functional inverses give us our inverse elements. So for any automorphism sigma, there is automatically a sigma inverse, which undoes it. And so when we're talking about this group, we're going to give this group a special name. And so the group of k automorphisms of L is what's called the Galois group of L over k, of the extension L over k. And we're going to denote it by this gal of L over k. Okay, and so Galois group, this is named after Galois, who really, spearheaded this study. And so we still call it that today. Okay, so now let's talk about what are some things that are true about these elements of Galois groups. And so we know that it's an automorphism from a field to itself. Okay, and so let's let K be a field. This is going to be our base field. We have alpha 1 through alpha n are all algebraic over K. And we're going to let L be the extension K adjoin alpha 1 through alpha n. Then, if we take any element of the Galois group sigma, we can know completely what it does to everything in L just by knowing what it does to these generators, alpha 1 through alpha n. So if we start off with alpha 1 through alpha n, we know that it generates all of L over K. Then by knowing what sigma does to alpha 1 through alpha n, this will tell us the whole map. And so in thinking about this, without loss of generality, we're going to assume that alpha 1 through alpha n is a minimal generating set for L over K. So what I mean by minimal generating set, it means that I need all of them in there to build all of L. Like if I take out alpha 1 and just look at K adjoin alpha 2 through alpha n, that doesn't give me all of L. I need alpha 1 in there. Similarly, I need alpha 2 in there. I need alpha n in there. I can't just pull one of them out and still keep the same field. So they all are necessary for building L over K. Well, so then thinking about this, so since there's only a finite number and they're all algebraic, this is a finite extension. And so as a vector space, there's only finite dimension there. And so we can talk about, taking elements of beta, how we write them in terms of alpha 1 through alpha n. And so essentially for anything in L, we can write it as a polynomial in alpha 1 through alpha n, where all the coefficients are coming from K. And so this is the way that I am expressing this right here. This beta equal to the sum of C1 alpha 1 to some power times alpha n to some power. Here I'm really talking about this is a polynomial in alpha 1 through alpha n. So anything that's in the field, if alpha 1 through alpha n are generating the extension, then anything in the extension can be written as a polynomial between them. And so then if we look at sigma of beta, well, so remember that sigma is a field isomorphism. It's an automorphism, so it's a field isomorphism. And so in terms of the sum, if I do it onto the whole sum, I can actually break it down to each of the summands, but then I can break it down to each of the parts, right? And the CIs, these are in K, and so they're fixed by sigma. And so I don't have to write sigma of CI, I can just write CI. Similarly, if I have sigma to this, monomial alpha 1 to a power times up to alpha n to a power, well, by the rules of isomorphisms and homomorphisms, I can distribute that alpha all the way through and get it down to the point where it's actually sigma of alpha 1, and then pull the power out, times sigma of alpha n, pull the power out. And so knowing what these are, what all of the sigma of each of these are, tells me what sigma of beta is going to be. Now, what about uniqueness? So let's suppose that we have two elements of the Galois group, sigma and tau, and that we have that sigma of alpha I is equal to tau of alpha I for all I. So that means that sigma and tau send each alpha 1 through alpha n each to the same thing. Well, so if we go back and look at sigma of beta, write it out the same way as we had it before. Now all of these sigma alpha i's are equal to the tau alpha i's, and so we can start distributing these in to the sum. And so we end up with ci times tau of alpha 1 to its power times tau of alpha n to its power. But then that's exactly the same thing as if we just did tau of beta. And so this is what gives us the uniqueness. So if sigma and tau send each of the alpha i's, each of the generators of the extension, to the same place, then they had to have been the same automorphism to begin with. And so this tells us that in terms of thinking about what these automorphisms do, all that we need to focus in on are these generators of the field. Once we know what it does to each of those, then that tells us everything that we could possibly want about the automorphism. So let's think about one concrete example of this, the complex numbers over the real numbers. Okay, and so one of the things we talked about before is that we can think about the complex numbers as just being the real numbers and then adjoin the imaginary number I in it. And this is something that we saw by the fundamental theorem of algebra, that all the complex numbers are just polynomials in R in I. Well, I, its minimal polynomial over the real numbers is x squared plus 1. And so I is the root of it, and minus I is the other root. And so this is just coming from x squared plus 1 is equal to x minus I times x plus I. And so I is our only generator for this extension, and there's only one other place I can go, which is to minus I. And so if we take any map, the only choices for I is for I to go to I or for I to go to minus I. So what does this tell us about the Galois group of the complex numbers over the real? Well, it only can have two elements, since what happens to I determines the whole automorphism. The only possible automorphisms of the complex numbers that fix the real numbers are the identity map and then the map that sends I to minus I. And this map that sends I to minus I, this is more what we would more commonly call complex conjugation. And so the only automorphisms on the complex numbers that fix the real numbers are the identity map and complex conjugation. So a corollary from this idea is that if you have a finite extension, if L over K is finite, then the Galois group has to be finite as well, right? So finite extensions give finite Galois groups. Okay, and so the thinking here is if L is finite, then we can write L, same as what we saw before, as K adjoin some finite number of elements. Okay, and so if L over K is finite, there is some alpha 1 through alpha n such that L is equal to K adjoin alpha 1 through alpha n. And each of these are algebraic over K. What's important about each of them being algebraic over K is that each of them have some minimal polynomial of finite degree, and so there's only finitely many other roots for each of them, right? So each alpha I only has finitely many other, and what we call them are conjugates, that it can be sent to. And what we mean by a conjugate is that a conjugate of alpha I is something that is a root of the same minimal polynomial as alpha I. So the conjugates of alpha I are all the things that have the same minimal polynomial of alpha I. It's all the other roots of that minimal polynomial. Alpha I can only be sent for a K automorphism. Alpha I can only be sent to something else that is the root of the same minimal polynomial over K. So there's only finitely many places for alpha I to go. Well, since any element of the Galois group is uniquely determined by what happens to alpha 1 through alpha n, and each of them only have finitely many places to go, well, at this point, this is just sort of like a probability problem, right? You think about how many choices alpha 1 has to go, how many places alpha 2 possibly has to go, You find out that there's only finitely total many possible such sigma. Okay, and so we only have finitely many such sigma. Okay, final theorem for this. So we've kind of been talking about what are the properties that that elements of the Galois group have, that K automorphisms have to have. Now we're going to do a sort of an existence theorem. And the existence theorem says, let K be a field and let alpha 1 and alpha 2 be roots of the same irreducible polynomial over K. And so this is the same thing as saying that alpha 1 and alpha 2 have the same minimal polynomial, because the irreducible polynomial would have to be the minimal polynomial. And let's say, suppose more, that alpha 2 is inside K adjoint alpha 1. Then there is going to exist an element of the Galois group of K adjoint alpha 1 over K that sends alpha 1 to alpha 2. So sigma of alpha 1 will equal sigma of alpha 2. So it says that not only alpha 2 is one of the possible places that alpha 1 could go, and this is saying beyond that, not only can it go there, but there is some element of the Galois group that does send it there. So let's start off thinking about some examples of this. So one would be, if we think about square root of 5 and minus square root of 5 over q. So these are both roots of x squared minus 5. So this is an irreducible polynomial over q, right? And so that means that if we look at q adjoin square root of 5, well, it's quadratic. It factors into x times square root of 5 times x plus square root of 5. And so the only possible place that square root of 5 could go is to minus square root of 5, other than itself. And what this theorem says is that there is, in fact, an element of the Galois group that does this. So if we're looking at q adjoint square root of 5 over q, looking in the Galois group, this is going to have two elements. It's going to have an identity element, ID, and then it's going to have some sigma, and sigma is going to send square root of 5 to, not sigma, to minus square root of 5, right? And so then we can ask, well, what does sigma do to minus square root of 5? Well, minus, we can think about that as being minus 1, and so we can pull the minus sign out. So it'd be sigma of minus times sigma of square root of 5, and so we'd have minus square root of 5, because sigma of square root of 5 is minus square root of 5, which gets us just back to square root of 5. So what sigma does to square root of 5 and minus square root of 5 is flips them, right? And so we can think about this: square root of 5, sigma sends it to minus square root of 5, and then sigma sends minus square root of 5 back to square root of 5. And so we can see that sigma here, as a cycle, it's a 2 cycle. It has degree 2, or has order 2, and that's it. That's the only possible. The only possible thing that can happen to square root of 5 is that it can go to minus square root of 5, and we're done. So let's look at a slightly more exotic example. So here, this omega here, this that looks like W, we're talking about this as being a cube root of unity so omega is equal to e to the 2 pi I over 3. And so the cube root of 2 is algebraic over this. And its minimal polynomial is x cubed minus 2. And it gives us our three roots, x minus cube root of 2. And then it has the two complex roots. One of them is omega times the cube root of 2. And the other one is the other cube root of unity, omega squared times the cube root of 2. And so if we adjoin the cube root of 2 to q adjoin omega, we're going to have the cube root of 2 in there. But since omega is in there, it also is going to give us these other two roots. And so now all three of these roots of x cubed minus 2 will be in this extension q adjoin omega cube root of 2. Okay. And so what the theorem here is saying is that there's going to be some sigma that sends cube root of 2 to omega cube root of 2 and then to omega squared cube root of 2. So let's think about what the structure here is. Let's clear out some space. Okay, so what the theorem says is that if we look at, there's some omega that sends cube root of 2 to, well, let's pick one of the other roots. Let's pick omega cube root of 2. So that's a different root of the same minimal polynomial. Well, this is this sigma here is in the Galois group of, so our k here is q adjoin omega, and so this really is q adjoin omega cube root of 2 over q adjoin omega. Okay, and so the sigma fixes all the elements of q omega, so that means that it fixes all the rational numbers and also anything with omega, any omega here, but it doesn't fix the cube root of 2. So if we look at sigma and apply it to omega cube root of 2, well, we can think about it as sigma applied to omega times sigma applied to cube root of 2. Omega is in cube root join omega, and so it's fixed by sigma. So we're just going to get another omega, so that's just going to spit omega back, and then we define sigma to send cube root of 2 to omega cube root of 2. So sigma of cube root of 2 is going to give us omega cube root of 2. And so what have we ended up with? Omega squared cube root of 2. And then similarly, if we look at sigma of omega squared cube root of 2, and we break it up, sigma is not going to do any, omega squared is in q adjoin omega, so it's fixed by sigma. So we're going to get an omega squared still out of that. And then we have sigma of cube root of 2 again, and so we get another omega cube root of 2, which gives us omega cubed cube root of 2. And so omega cubed cube root of 2, well, omega is a cube root of unity, so if we cube it, this is just 1. And so that disappears, and we end up just with cube root of 2. So let's think about what this sigma is doing as a permutation on these roots. So sigma sends cube root of 2 to omega cube root of 2. And then we worked out that sigma sends omega cube root of 2 to omega squared cube root of 2. And then lastly, if we apply omega to omega squared cube root of 2, we get back just the cube root of 2. So omega permutes these in a cycle just like this. Cube root of 2 goes to omega cube root of 2, which goes to omega squared cube root of 2, and that's it. So let's prove this, and really the proof here, it's really just tying together a couple of ideas that we've seen over the last couple of videos. So the first one is to note that there is an isomorphism between K adjoin alpha 1 and K adjoin alpha 2 that fixes K. And this isomorphism is going to send alpha 1 to alpha 2. And this all boils down to how we thought about these rings to begin with. And so it boils down to that K adjoin alpha 1, well, this is isomorphic to the polynomials over K modded out by the minimal polynomial for alpha 1. But since the minimal polynomial for alpha 1 is alpha 2, this is then isomorphic to K adjoin alpha 2. And in this isomorphism, as we're looking through this chain from alpha 1 to K adjoin X modded out by the minimal polynomial to K adjoin alpha 2, well, from the way we talked about at the beginning, the isomorphism is between alpha 1 and X. So alpha 1 is getting mapped to X, and then the isomorphism between K adjoin X modded out by the minimal polynomial to K adjoin alpha 2 is sending X to alpha 2. So composing these two isomorphisms together, we end up with this map sigma that sends alpha 1 to alpha 2. So we do have an isomorphism that sends alpha 1 to alpha 2. Now what we need to prove now is that this really is a member of the Galois group of K adjoin alpha 1 over K. And so we know that alpha 2 is inside K adjoin alpha 1. This was one of the things that we supposed to be true in the statement. And so if alpha 2 is inside K adjoin alpha 1, then I can do any polynomial in alpha 2 using coefficients of K and still stay inside K of alpha 1. And so this tells me that K of alpha 2 is a subfield of K adjoin of alpha 1 because it contains alpha 2. Well, now we can do the Tower law just to show that this is going to lead to K adjoin alpha 1 being equal to K of alpha 2. So how does this work? So by the Tower law, at this point we have K is a subset of K adjoin alpha 2 is a subfield of K adjoin alpha 1. And so then the Tower law says that the degree from K to K adjoin alpha 1 is going to be equal to the product of the degrees between K adjoin alpha 1 over K adjoin alpha 2 and K over K adjoin alpha 2. Right? And so we're going to be looking at that product. But alpha 1 and alpha 2, they have the same minimal polynomial. And so the degrees of their minimal polynomials are equal to each other because it's the same polynomial. And so that tells us that the degree of these extensions are the same. And so K adjoin alpha 1 over K has to equal K adjoin alpha 2 over K. And that means that the degree of K adjoin alpha 1 over K adjoin alpha 2 has to just be 1 because these two factors are equal to each other. And so this one has to equal 1 in the middle. Well, if it equals 1, and this is a problem that you had for homework, any extension that's degree 1, they're the same field the whole time. And so this tells us that K adjoin alpha 2 is equal to K adjoin alpha 1. And so this sigma that sends sigma of alpha 1 to alpha 2, where sigma was going from K adjoin alpha 1 to K adjoin alpha 2, Well, since sigma is an isomorphism and K adjoint alpha 1 and K and alpha 2 are the same field, this is, in fact, K of alpha 1. Not only are they isomorphic, but they are the same thing. Then sigma really was an K automorphism to begin with. So this tells us that sigma is in the Galois group of K adjoint alpha 1 over K, and that gives us our existence. That is all for this video. I hope you enjoyed it. I will see you again soon.